Testing, can you hear me? Hello. All right, this video is public now. So I'm going to be studying binary trees again. Last time I studied about tree traversal. That's the last topic. Just want to, I just want to recap on full and complete. Where is it? So a full binary tree is either an internal node with exactly two non-empty children or a leaf. Okay, so leaf. So you cannot have a node with one child. Has to be 2 or 0. A complete binary tree has a restricted shape obtained by starting at the root, winning the tree by levels from left to right. Alright, so the tree, when we are adding to a tree, we are adding from the leftmost side. And then we are filling it up. Also, I tried to implement a binary tree. I'm going to redo this. So, hold on. This is quite confusing. These are the values I want to fill. Uh, I'll just put that here for now, temporarily. So I have the initialize and get tree, binary tree node. I should write complete tree node. Complete binary tree node. Complete binary tree node. It's even longer name. So I have the complete binary tree. I initialize and get the tree. So basically, I just make the root of the tree. I set the value. So I initialize and get tree value is 20. So I get the value, the left subtree is null, right subtree is null, and I return it. And then the function I want to implement is this one, add to tree, which will have the value 5 and 10. I'm trying to get these values into the tree. Uh, Complete binary. So it's going to be a complete binary tree. And I will add the values left to right. But let me think about how I should do this. A complete full tree. Complete. I want a word that describes like a tree being completely filled. There's full tree, there's complete tree. Okay, I will describe a word called filled tree. So a filled tree, right? So here is a subtree. This subtree is filled if it has two. If it's like if all the nodes at a particular depth are filled. So there are 4 nodes here. You can't have one node missing. So so by filled, I mean you can't have children missing. That's what I mean. So when I add to the tree, I start with the node. I check whether the left subtree is filled. If it's not, then I check whether the right subtree is filled at the same height as the left one. So the left one, 1, 2 has a height of 2. The right tree is not filled at the same height. So it needs to add a child. So next time I add a child, I add it over here at the same depth. That's what I'm thinking. And hold on, I just want to test something. All right. I was just checking my controls. Anyways, um, add tree, add to tree. So what I will do is check whether the left is filled. Complete binary tree, left subtree filled. There's no boolean though. So I'll just use int left subtree filled, and then similarly right subtree filled. Both of these will initially be 0. So we are going to add the left subtree. The left subtree is filled. Add to tree. So first we make a new node. New node or a new tree, and then for this new node it will have the value. It will have, yeah, it will have these values. New node. Oops. V it will have these values, and the question is way to add it. So there needs to be a recursive way. Check whether the left subtree is null or right subtree is null. Yeah, there needs to be an add node void add node. Um add node int val. This add node should go in here. Add node, and then node becomes the new node. Yes, now we think about the traversing aspect. So we start with the root, add to tree. If the the tree if the tree, let's put tree node. If the left subtree is empty, left is empty, then add the node on the left side. Else if the right one is empty, then add it to the right side. Now the question is the root has only two levels, right? So I start with the root. I add it to the left initially. The left is filled, so I add it to the right. If both the left and right are filled, I check the left subtree. If both the left and right are filled, um, I think I should start by checking the left subtree or the right subtree. So, so I should check whether the left subtree is filled. Do we even? We don't need this. We don't need the right one. We just need the left one. If the left subtree is not filled, then we add the node to the left. Let me think about this. But the thing is, you're checking over here. How do you check whether this side is filled? How do I check that? How do I check the same height? You know, the I don't know how to describe it. Like, how do you know if you're currently over here? How do you know supposed to start a new one or you're supposed to go to the right? You check whether the left is filled. If it is filled, if filled is one, then you check the right. Okay. The left is not filled over here. So you go to the left subtree. The left is not filled. If the left is 0, if the left is 0, the left is not filled. Then you add to the left subtree. I have an idea. If this current tree node is null, if current tree node is null, then you add the node. Then you add the node to it. So you go left. So initially we start with 0. We go in, so both of these are null. We go left. There's nothing here. We started, and then we say that the left is filled. The left is filled. Add node left. The left is filled. So from the root, as from the root side, the root node itself is filled. So it will go to this if condition. The left subtree is not filled. So add to tree, add to tree, add to tree. Let me think about this. Add to tree. Should I have the right subtree filled variable or not? Tree node left subtree filled. We add a node over here. And then the left subtree is filled. But then how would we know when it's very deep? Okay, in this case, for the root, it should say left subtree is not filled. For this node, it should say left subtree is filled, so it should go to the right. And then for this node, it should check both the children. Oh, I have an idea. First, it should check both the children. One of the child is missing, fill it in. But if both the children are available, check whether the left subtree is filled. Okay. So first of all, if left subtree, left subtree, else right subtree. You add the node. So let's think about this. So if left subtree. So we start with the root. Left is nothing. So you add the node and add the new value to it. Next time we come here, left is filled, but the right is not filled, so it will add to the right. Right? Now, next time it comes here, both the children are filled. If both of them are filled, check whether the left subtree is full. And it's a 0, so it's not filled, right? So if it's not filled, it will go to the left first. How is the adding done? Or maybe I'm getting this wrong. Maybe what if I don't need to add it in order? What if I add it in a sorted order? So we check the value. No, but I want a complete tree. I want a complete tree. So left subtree is not filled. Left subtree is not filled, so fill it. And left subtree is not still not filled, so fill the children. We fill the right one. And then we say that the left subtree is filled. We fill the right subtree. Okay, I will think about this later. Maybe I'm getting it wrong. Uh, Also, they talked about the traversal aspect. That's also what I learned. So, pre-order traversal. Pre-order is like the parent first. So, you want to print these values. You go through the tree. You print the parent first, and then the left child, and then the right child. So for f h I over here, you print f first, then you go left, print h, and then you can't go any more left. So you go right, you print I. So going from A, you print A itself first, then you go left, print B. There is no left, so you go right, print D. Now keep going back, go right of A, there's C, go left, there's E, go left, there's G. Now there's no right in E, there's no left right in G, there's no right in E, but there is right in C. So F, H, and then I. So it's left, so it's parent, left, then right. So for post order, it's left, right, then parent. So you go left, there is no left, you go right, print D. You go back, print the parent, go back, print the parent. We already visited left, so we go right, print the, no, don't print this, go left, G, E, C, and then we go right. We don't print the parent, we print left, right, and then the parent. And then finally we print C and then we print A. And then in order traversal, it's left, parent, right. So left, there's no left, so we print the parent and then we print right. Wait a minute. We print the parent and then we print right. Yeah. Then we go back up, print the parent, and then go left, print this, print E, there's no right, print C, and then go right, left, H, I, and then F. So value, set value, left, right is a leaf. Is leaf, is leaf, is a leaf. Is a leaf. So left subtree. Okay, I'm going back to this. Check whether left is empty. Add to left. Check whether right is empty. Add to right. And then left subtree fill is 0. Since it's 0. Since it's 0, then print left, and then since it's still 0, print right. And then the left subtree fill should be set to 1. Let me think. Or maybe there should be I have an idea. We start with the root. We fill the next time we start with the left and then with the right. And then we call this root node full because it has both the children. then full, then this is not full, then put here. But the thing is, when you're in this node, how do you know you're supposed to, like when you're in this node, for example, how do you know you're supposed to go bottom? You're supposed to add here, or are you supposed to add here? I wanted to fit it from left to right. And not overly complicated. Or maybe I should save like a global height value. So the height of this is the height of this. No, height wouldn't work. Hold on. Should I save a height value? If the height of this is 4, 1, 2, 3. How do you check the minimum height? The minimum height is set to 2. So 1, 2 here. Minimum height is set to 2. Maybe a minimum height would work. If the minimum height of both of these, 1, 2, 2, 1. Wait. No, it shouldn't be minimum height. It should be filled or not filled. Like I did with the left subtree. Okay, never mind. The examples they're giving, the trees are already filled though. You already read this chapter, implementing tree traversal, but the examples are already filled. That's the issue. Consider the problem. Secret to success when writing a recursive function is not to worry about how the call works. Just accept that it will work correctly. One aspect of this principle is not to worry about checking your children when you don't need to. You should only look at the values of your children if you need to know those values in order to compute some property of the current node. Child value should not be used to decide whether to call them recursively. Make the call and let their own base case handle it. Consider the problem of incrementing the value of for each node in a binary tree. Calling solution has an error since it does redundant manipulation to left and right children of each node. Set value plus 1. Left is not null. Set value. Setting the left value to plus 1, but then you're going to left. And then when you do go to left, the left again it increments by 1. I think they should remove this part and this part. Information flow in recursive functions. Adding information flow in a recursive function can be challenging. In any given function, we might need to be concerned with either or both of passing down the correct information needed by the function to do its work, returning information to the recursive function's caller. Any given problems might need to do either or both correctly. Here are some example and exercises. Local traversal involves going to each node in the tree to do some operation. Some functions need no information from the parent and pass no information back. Examples include pre-order traversal and incrementing the value of every node by 1. Slightly more complicated is the situation where every node needs to pass the same piece of information. Where every node needs the same piece of information to be passed on it. An example would be incrementing the value for all nodes by some amount. In this case, the value parameter is simply passed on unchanged in all recursive call. Many functions need information that changes from node to node. An example is a function that's set to set the value for each node of the tree to be its depth. In this case, the depth is passed as a parameter to the function, and each recursive call must adjust that value. Collect and return requires that we communicate information back up the tree to the caller. Simple examples are to count the number of nodes in a tree or to sum the values of all the nodes. Consider the problem of counting the number of nodes in a binary tree. The key insight is that the total count for any subtree is one of the root for the root plus the counts for the left and right subtrees. Where do the left and right subtree come from? Calls to function count on the subtrees will compute this for us. Thus, we can implement count as follows. Count left plus right. So if it's root, return null. Return 1 plus count left plus right. The following solution is correct but inefficient as it does redundant checks on the left and right child of each visited nodes. Oh, the left and right might be empty. Is that what they mean? This is the inefficient count. So count 0. If left is null, then we do this. If right is null, then we do this. If both left and right is null, then 1. Okay, I see. When you write a recursive function that returns a value such as counting the number of nodes in the subtree, you have to make sure that your function actually returns a value. A common mistake is to make a recursive call and not capture the returned value. Another common mistake is to not return a value. Oh, they forgot to return. Last time I did these exercises, my stream stopped. So that's why I'm just skipping these through. Many functions require both that information be passed in and that information be passed back. Let's start with a relatively simple case. If you want to check if some node in the tree has a particular value, that value has to be passed down and the count has to be passed back up. The downward flow is simple as the value being checked for never changes. The information passed up has a simple collect and return style. Return true if and only if one of the children returns true. Slightly more complicated problems combine what we have seen so far. Information passing down the tree changes from node to node. Data passed back up the tree uses the collect and return paradigm. The height of a binary tree is the length of the path to its deepest node. Binary tree node implementation. Value set value left right is leaf. Wait, I just got an idea. How about instead of left tree right tree filled, we do minimum height and max height. Minimum height is 0, max height is 1, 0. And then when we add the node, we do this, and then we completely remove this. Okay, so this is what I'm thinking. Not root, new node. So we start with minimum height, maximum height 0. If they're both 0, then you go left. Then we go left. If the left one is empty, we add a node. Okay, let me do it here. So the root will contain minimum height, maximum height. Minimum height is 1, 2, and then empty. Minimum height is like when do we reach the empty node first, and then maximum. Then 1, 2, 3. This is the maximum height. Maximum 1, 2, minimum. So the root will check if the left or right is empty. The left is, so we start with the root. Check left and right is empty. If left is empty, fill in the left. The right is empty, fill in the right. If both left and right are are there, then we check. Then we check. Um. Then we check whether there's a mismatch between the minimum height and the maximum height. Minimum and maximum on the root are the same because they're both 1. So we go to the left. The left fills in this, and then next time it repeats the same process. The left fills in this. Wait, no, hold on. The minimum height and the maximum height. Maximum becomes 1, 2 becomes 2, and then minimum becomes just 1. Then we go left. No, we check this for the left thingy. Hold on, let me think about this. Okay, if the minimum and the maximum are equal, the minimum and the maximum are equal, we go left. So the base case is that if we see a node, add to the left. If the left is filled, add to the right. Right. But if that's not the case, you check whether the minimum and maximum are the same. If they are, just go left. Minimum, maximum, same, go left. Minimum, maximum, same, go left. Minimum, maximum. There's no minimum, maximum, just add to the left here. And then when we do a recursive backwards, we increase this by 1. When we do recursive backwards, the maximum height increases by 1. But uh, if there's a mismatch, minimum height, maximum height, if there's a mismatch between the two, 1, 2, 3, 4. Sorry. 1, 2, 3. 1, 2, 3, 4. There's a mismatch. You check if there's a mismatch with the left. 1, 2. 1, 2, 3. You check if there's a mismatch on the left, then you go left. There's no mismatch on the left. If there's no mismatch on the left, then you go right. I think. Okay, let's try to implement. Maybe it's more complicated than it should be. Uh, if minimum height and maximum height are both 0, no, actually just to the, okay, this is what I'm going to do. You add the left one, left subtree. If this is null, if this is null, then you add it, then you add the node to it. This is null, add a node to it, add a node to it, and you add it to the left side, the current side max height is incremented by 1, right? If the immediate right tree is null, right tree is null, then you add it to the right one and you increase the minimum height. So minimum h, maximum h, both are 0 at first, you add to the left, so this becomes, the maximum becomes 1. If the right is empty, the minimum becomes 1. Add to the right, make the minimum 1. So far, so good. Now, if these two matches, we just go to the right. We just go to the left, and then we do the entire thing with the left. As if the minimum height matches the max height, then just go to the left. Height, maximum height. We go to the left. But the thing is, when we do go to the left, eventually, when you go to the left, eventually a node will be added, so the max height will increase. We go to the left, eventually a node will be added, so the max height will increase. The minimum height, wait. Minimum height is 0. Maximum height is 1. Maximum height is 1. If there's a miss, if it matches, just go to the thing. Just go to the next one. If there's a mismatch, you still go to the left. You still go to the left. And you check whether there's a mismatch in the left. If there's no mismatch in the left, then you go to the right. There's no mismatch on the right. No, that can't be possible. There's mismatch on the root, either the left, there's either a mismatch on the left or on the right. So go to the left. So if there's a mismatch here, you go to the left. There's a mismatch here. It's not necessary that the minimum height will increase. Could be either the minimum or the maximum. We go to the left. If it matches, go left, left, and the max height will definitely increase. But if there's a mismatch, check if there's a mismatch over here. Then the minimum height will no, it won't necessarily. No, it is 0. Left, 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 left. Or should I have a global? No, I should avoid global values. Do they have implementation of one node or do they have the implementation of the entire tree? They have one node, right? Yeah, left, right. I understand that, but how do you add? They keep talking about traversal. They don't talk about adding an element to a complete thing. What if I do this? What if I do a greedy method? Greedy method where I start by going to the right and check if it matches the height of the tree. If it doesn't, go. If it doesn't, then I go left. Yeah, I keep going left in the same depth, right? Until I can no longer go left. Hold on. Imagine there was a mark here. There's a mark here. Go here. Fill these in. No, but that doesn't make any sense. How do you know? No, wait, that does make sense. If both of them have a mark, both of them have a mark. Hold on. Either left or right is empty. Just fill in the values. If left, keep going left. But if it keeps going left, it will keep adding like this. We don't want that. Um, we could 1, 2, 3, 4. The math we did with the number of leaves, we could take that into use maybe. 1, 2, 3, 4. Minimum height, maximum height, maximum height. Okay, I will write the minimum first, then maximum. So 1, 1. Minimum is 1, maximum is 2. And then here, 0, 0. Minimum 0, maximum 1. There's a mismatch here. Is there a mismatch on the left? So we go left. But the thing is, if the left is filled, if there's no mismatch on the left, then we go right. Let's try it over here. 1, 1, 2, 3. 1, 2, 3, 4. There's a mismatch here. There's no mismatch here. This is about 3, 3. The mismatch here. 1, 2. There's no mismatch. You don't even look at the right part. You just go there. Mm, the left subtree is completely filled. The right subtree is completely filled. But this depth, though, that's the issue. Like, how will the program know that you have to add an extra here? Maybe I should record the depth of the thing. Not depth, not the height. The minimum height. So 1, 2, 3, 4, 4, 3, 1, 2. So this should be the minimum height minus this. Then that means this is to its fullest. If the minimum height here is 3, the minimum height here is 2, then that means it's not to the fullest. Here it's 1, but this 1 less is. But the thing is, this node has the height of this node is 1 less than the height of this node. Okay, maybe it's more complicated than it seems. Maybe I'm making it more complex. Here is some implementation for the bin node interface, which we will name BST. Well, what is binary search tree? Its element type is an object when you need to support search structures such as the binary tree search tree. The node will typically store a key value pair. Every BST node object also has two pointers, one to its left child and another to its right child. Some programmers find it convenient to add a pointer to its parent's node, allowing easy upward movement in the tree. Using a parent pointer is somewhat analogous to adding a link to the previous node in a depending list. In practice, the parent pointer is almost always unnecessary and adds the space overhead for the tree implementation. And, it is not a problem that the parent pointers take space. It is not just a problem that parent pointers take space. More importantly, many uses of the parent pointer are driven by important improper understanding of recursion and so indicate poor programming. If you're inclined toward using a parent pointer, consider if there is more efficient implementation possible. Another important decision in the design of a pointer based node implementation is whether the same class definition will be used for leaves or and internal nodes. Using the same class for both will simplify the implementation but might be an inefficient use of space. Some applications require data values only for the leaves. Other applications require one type of value for the leaves and another for the internal nodes. Examples include binary, how do you pronounce this? PR quad tree, the Huffman coding tree, and the expression tree. By definition, only internal nodes have non-empty children. If we use the same node implementation for internal and leaf nodes, then both must store the child pointers. But it seems wasteful to store child pointers in the leaf nodes. Thus, there are many reasons why it can save space to have separate implementations for internal and leaf nodes. Yeah, I think I suddenly got an idea. I got an idea. We store the number of leaves. So if there is one root, there should be two leaves to be completely filled. There are two leaves. Now, if I want to add any new, um, this has two leaves, four leaves, and then eight leaves. Eight leaves, okay. So we start with the root. We start with the root. If both the children, there will be a leaf property, leaves. There should be potential leaves property. How many total leaves are possible? Which in this case, let me just remove this over here. In this case, it is 8. Why does it add this? In this 8, which is 8. If I want to fill this up, I need to fill it up with 8. But if I go to the first child, potential leaf, potential leaf will be 1, 2, 3. It would be 4. So this one is completely filled. Over here, potential leaves. Potential leaves is 4. There should be potential leaves and how many leaves are actually filled. So leaves are 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. 7. If there is a mismatch, if there is a mismatch, then we go down here. Then we check where this mismatch is. If there's a mismatch here, then we leave it. Sorry, if these two matches, then we leave it. Then we go to the other child. If these two don't match, then this is the place we go. Then we check the left child, potential leaf matches the actual number of leaves, which is 2. Then we go here, potential leaves is 2. And then leaves, the actual number of leaves is 1. So we add one more. Now here's the thing. Once this is completely filled, once this is completely filled, once this is completely filled, then what do? We increase, if this is filled, we increase the potential leaves by 16. And then we go down, we just go down to the left one. These two are equal. We increment it by 8. Is that right? No, that's not right. I think I made it more complicated, maybe. Mm, we don't need potential leaf. We just need leaves. We just need leaves. So the number of leaves, 1, 2, 3, 4, 5, 6, 7 is 7. Um, it is 7. 7. So it is supposed to be divided into 4, 4. Hold on, let me think this through. If this is filled, now 1, 2, 3, 4, 5, 6, 7, 8. 8 leaves, but 1, 2, 3, 4. But a depth of 4. There's a depth of 4. Uh, 2 to the power of 0 is 1. 2 to the power of 4, 16, right? Or am I getting that wrong? Yeah. So first we calculate 2 to the power of the depth, which is 4, which is 16. And then we go here. We have 1, 2, 3, 4 leaves, and the depth is 1, 2, 3, 1, 2, 3. So 2 to the power of 3 is 8. 2 to the power of 3 is 8. Then we go here. Wait, if this was filled, how would it work? Depth is 4. To the power of 4 is 16. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 to the power of 4 is 16. Um, you need 16, right? Half of 16 is 8. I forgot what ES meant. Leaves is internal node plus 1. But it's supposed to be. If it's full, no, it's generally internal node plus 1, right? So what do I do with 9 and 4? 1, 2, 3, 4. The depth is 4. Leaves are 9. And now it's 10. 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. Okay, I think I have an idea. Uh, Hold on. So leaves are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, the depth is 4. In the subtree, the left subtree, check whether the number of leaves is half the depth. So 2 to the power of 4 is 16. Check whether the number of leaves is 8. If it is, you skip this, you go here. Uh, Go here. But the thing is, add the node 4 leaves, depth 2. 4 leaves, depth of 2. 1, 2, 3, 4, 1, 2. 2 to the power of 2 is 4. 4 leaves is correct. This have half of 4. This has half of 4. If it has half of 4, just keep going down. We increase the depth of by 3. And then we just go to the left one. Yeah, I think I have an idea, but I will just read this first and then I'll. Object-oriented languages allows us to differentiate leaf from internal nodes through the use of class hierarchy. A base class provides a general definition for an object. A subclass modifies a base class to add more detail. Base class can be declared for binary tree nodes in general, with subclasses defined for the internal and leaf nodes. The base class in the following code is named where bin node includes a virtual member function named isLeaf, which indicates the node type. Subclasses for the internal and leaf node types are each implement isLeaf. Internal nodes store child pointers of the base class. They do not distinguish their children's actual subclass. Whenever a node is examined, its version of its leaf indicates the node's subclass. Var x. Okay. Composite based expression tree. There is another approach that we can take to represent leaf and internal nodes, also using a virtual base class and a separate node classes for the two types. This is to implement nodes using the composite design pattern. This approach is noticeably different from the procedural approach in that the node classes themselves implement the functionality of traverse. Here is the implementation. Base class var bin node declares a member function traverse that each subclass must implement. Each subclass then implements its own appropriate behavior for its role in a traversal. The whole traversal process is called by invoking traverse on the root node, which in turn invokes traverse on its children. Where bin node is leaf traverse, leaf node, visit leaf node. Should there be a visited thing, a visited member? Do they have it? Visit operator. This module presents techniques for calculating the amount of overhead required by binary tree based on its node implementation. I want to check. Recall the overhead is the amount of space necessary to maintain the data structure. In other words, it is any space not used to store the data records. The amount of overhead depends on several factors, including which nodes store data values, whether leaves store child pointers, and whether the tree is a full binary tree. I want to check the node implementation again. Linear structure design binary, cursive definition. Uh, Maybe here. Where did they implement it? Where is the thing? The implementation, the interface where they show the binary tree. I want to see all the methods based on its node implementation. Define a node ADT to work with value, set value, left, right is leaf. Okay, there is a dumb way of fulfilling this. Instead of recording, do I traverse is leaf? Depth is 4, 1, 2, 3, 4. Depth is 3. I think the minimum height, maximum height is the way to go. I think. In a simple pointer based implementation, every node has two pointers to its children. This implementation requires total space amounting to n 2p plus t for a tree of n nodes. P stands for the amount of space required by the pointer. So there are two pointers. D is the amount of space required by the data value. But if they have no other information other than what the children is and what the node value is, then when they're adding a node, how do they know whether to go back or whether to fill the node in, fill the children in? Here, P stands for the amount of space required by the pointer and D stands for the amount of space required by the data value. The total overhead will be 2pn for the entire tree. Why 2pn? What about the data? Oh, just for storing the pointers. So data value is the actual thing we want to store, but the pointers and everything, it's 2pn. And then nd is what we want to store. Thus, the overhead fraction will be 2p divided by 2p plus d. The actual value for this expression depends on the relative size of the pointers versus data fields. If we arbitrarily assume that p is equal to t, then a binary tree has about two-thirds of its total space taken up in overhead. Worse yet, the full binary theorem tells us that about half of the pointers are wasted null values that only serve to indicate the tree structure, but which do not provide access to new data. In many languages, the most typical implementation is not to store any actual data in the node, but rather a pointer to the data record. In this case, each node will typically store three pointers, all of which are overhead, resulting in the overhead fraction 3p divided by 3p plus p. If only leaves store data values, then the fraction of the total space devoted to overhead depends on whether the tree is full. The tree is not full, then conceivably there might be only one leaf node at the end of a series of internal nodes. Thus, the overhead can be arbitrarily high percentage for a non-full binary tree. For, for non-full binary trees, the overhead fraction drops as the tree becomes closer to full, being lowest when the tree is truly full. In this case, about one half of the nodes are internal. Great savings can be had by eliminating the pointers from leaf nodes in full binary trees. Again, assume the tree stores a pointer to the data field because about half the nodes are leaves and half of the internal nodes. And because only internal nodes now have child pointers, the overhead fraction in this case will be approximately um, n over 2 2p divided by n over 2 2p plus dn is equal to p over p plus d. If p is equal to d, the overhead drops to about one half of the total space. However, if we only need nodes you store useful information, the overhead fraction for this implementation is actually three-quarters of the total space because half of the data space is unused. If a full binary tree needs to store data only at the leaf node, that a better implementation would have the internal nodes store two pointers and no data field, while the leaf nodes store only pointer to the data field. This implementation requires n by 2 2p plus n by 2p plus d units of space. If p is equal to d, then the overhead is 3p divided by 3p plus d, which is 3/4. It might seem counterintuitive that the overhead ratio has gone up while the total amount of space has gone down. The reason is because we have changed our definition of data to only refer to what is stored in the leaf nodes. So while the overhead fraction is higher, it is from the total storage requirement that is lower. One serious flaw with this analysis when using separate implementations for internal and leaf nodes, there must be a way to distinguish between the node types. When separate node types are implemented via Java subclasses, the routine environment stores information with each object, allowing it to determine, for example, the correct subclass to use when the isLeaf virtual function is called. Thus, each node requires additional space. Only one bit is truly necessary to distinguish the two possibilities. In rare applications where space is a critical resource, implementers can often find a spare bit within a node's value field in which to store node's type indicator. An alternative is to use a sparse bit within a node's pointer to indicate node type. For example, this is often possible when compilers require the structures of and objects start on word boundaries, leaving the last bit of the pointer value always zero. Thus, this bit can be used to store the node type flag and is reset to zero before the pointer is dereferenced. Another alternative when the leaf value field is smaller than the pointer is to reduce the pointer to a leaf with that leaf's value. Okay. Binary search tree BST is a binary tree that conforms to the following condition, known as the binary search tree property. All nodes stored in the left subtree of a node whose key value is k have key values less than or equal to k. All nodes stored in the right subtree of a node whose key value is k have key values greater than k. Figure 7.11.1 shows two BSTs for a correction of values. One consequence of the binary search tree property is that if the BST nodes are printed using an in order traversal, then the resulting enumeration will be sorted order will be in sorted order from lowest to highest. Okay. Here is a class declaration for the BST. Recall that there are various ways to deal with keys when comparing records. Three typical approaches are key value pairs, special comparison method such as using the comparator class and passing in a comparator function. Our BST implementation will require that records implement the comparable interface. So in Java, node count, null node count, and then we insert. First operation that we will look at in detail will find the record that matches a given key. Notice that in the BST class, public member function find calls private member function find help. Method find takes a search key as an explicit parameter and its BST is as an implicit parameter and returns the record that matches the key. However, the find operation is most easily implemented as a recursive function whose parameters are the root of the subtree. And the search key member find help has been has the desired form of this recursive subroutine and is implemented as follows. You want to visit the left child. Oh, it's ordered, right? So the lower ones go to the left, the high ones go to the right. And then once we find the key, it's the record, and then we unwind, go back to 32. Okay, and in my problem where I was trying to add a new thing, I should have a go right and go left. Actually, just go left is initially set to true. Go left is set to true, and then go left is false. False, and then over here we add. Oh no. So what I was thinking, maybe start with the root. There is an empty child, just fill one of them, and then next time as well. And then by default, go left is 1. Go left is 1, then we go left. If go left is 1, we add here. If go left is 1 still, here the right is empty. And then we go back, go left becomes 0. Go left is 0, then by default over here, go left is 1. No, I think if this, as soon as we see an empty child, we just add it to the child. We don't look at. Now going back. But somehow it needs to set go left back to 1 once this has been added. If the rightmost child is added, then go left needs to be set to 1 again. Um, how about I have event left variable, which returns if it went left or not. Okay, how about this? So the moment we see empty left, add it to the left. The moment we see empty right, add it to the right. Go left by default is 1. Both the children are filled. We go left. The moment we see empty left, we fill it. Empty right, we fill it. But then we somehow need to set this to 0. Um, huh. How would you know from here whether you're supposed to go left or right? Or what about the solution I had before, where the left subtree is filled? When we are unwinding, we check whether the tree itself is filled. Left subtree is filled. If it has both the children, we return. If it has 2 child, how about this? If it just added a right child, it returns a 1. Added to the child at right, it returns a 1. And in the parent case, say that the left subfield is full. Full is actually 1. If full is 1, Full right now is 1. If full is 1, if full is 1, set it to 0 and go left. Then the moment we go left, this, fill this, and then this full is 1. If the child full is 1, you go here. Child full is 1, we go here, fill this, and the full becomes 1. And both of them are 1. If both of them are 1, if both of them are 1, then we set both of them to 0. And then we go left. I think that might work. Let me think about this. Here full is 0. Check the child. If full is 0, check if full is 0. Check the left one. If left one is 0, check the left one. If left one, check the left one. If left one is 0, go down and then just fill this in. Starting up here, left, go right, fill this in. Then set full to 1. Full is 0. The left one, full is 0. Right one, full is 1, so go right. Okay, wait a minute. Full, full, full. Complete binary tree are at the root. We are at the root, right? If we are at the root, then the moment the right, we added a node to the right side, then tree node full becomes 1. Tree node full becomes 1. Hold on. So full is 0. We add to the left. The moment we add to the right, this becomes 1. And for these two, the full is 0. But when we reach the thing, when we reach it, if it's full, else, if it is full, if it is full, then what? We are at the root node, it's full. Then set the full to 0 and go left. Set the full to 0, go left. Full. Set the full to 0, go left. And then this algorithm will work with the left subtree, what we did with the right. If this is 1, set full to 0, and then go left. And the left adds thing. When it goes left, left subtree is empty, so add here. And then right subtree is empty, add here. So this is how it adds the next two values. I'll just write f. I'll just write, I'll just, if it's 0, I'll just write f is 0. Or I should color it down. I think that would be easier. Well, if it is full, full is 0, full is 0. Here full is 1, so we add this. Because when the right one gets added, it becomes full. So we do this. And then when we unwind, we go back. Full is 0. And then next time we want to add a new value. And add a new value. We check if it is full. It is not. We set it to 0. But if it's not, it checks the left subtree. It checks whether the left subtree is full. It checks whether the left subtree is full. If the left subtree is full, go to the right one. Left subtree is full, go to the right one. And then the entire algorithm starts again. Not full, we just add left, and then next time we add right, and then this becomes full. And then next time you start with the tree again, full, full, this becomes full. Yeah, full, full. This, but instead of making it full, we go to the left and set it to, hold on. We go to the left and set the full to null. We set the full to null, and then the entire thing with the left side keeps happening. So full is null, 0, 0, and then full. And then we go right, add, null. And then when it goes back, this becomes full, right? And both the left and right are full, then this becomes full. Let me think. Or I have an idea. The moment right becomes full, we make this tree full. Voila. Add node. Add node to the right subtree. Add node to the right subtree. Add node to the right subtree. If the right subtree is full, then this tree node becomes full. Then this tree. So next time when we are adding, we see it's already full. We set the full to 0 along with both the children. We set the full to 0 and then we just go left. So next time we come here, tree node is full, set the full to 0 and then just go left. I want to see if it's being done correctly. Can I paste? I can paste. Okay, so let's do this. So we start with the empty. We start with empty, a single root. Tree node is not full. Of course, there's no left tree or right tree. Um, Wait, I should check the left and right first. I should maybe I should do this first. Check the left and okay, yeah. Check the left and right. How do I? Yeah. So a tree is not full. Check the left and right. We do check the. I okay. Why does it? We do check the left. Check the left. We add it to the left. Now next time we add, if the left subtree is already, if there is something on the left subtree, we add it to the right. And when we do add it to the right, this node becomes full. Now the next time we add, node is full, and then we just go to the left. And then this algorithm works with the left again. Add here, and then next time we add, this is not full. Next time we add, tree is, this is not full. So we need to go left. So this is not full. This is versus tree no left tree full. Else if tree node left tree full. Tree node left subtree full. If it's not full, we go. Okay. If it's not full, then go left. Go left. No, I need to. Yeah. So if it's not full, just uh, they look here not full, then we go left. And then when we do go left, this part will turn true. Now, when this part runs, tree node becomes full, and then it ends. So next time when we add tree node full, tree node left subtree, this. So tree node left, this is full. So then that means if this is full, then we go right. If we go right, then that means we go right. I think this is an error. I shouldn't be doing this. Then we go right. Then, yeah, once we are at right, this will activate. And of course, next time we add, this will activate and the tree becomes full. And when it unwinds, if it unwinds, this tree becomes full. If it unwinds, If it unwinds from here, and then the right subtree becomes, what was the previous thing? Right sub, no, I think this was correct. I think this was correct. Hold on, let me. Okay, so first of all, start from, we add a new node. This is full. Uh, yeah, this is full. So we go right. And then when we go to the right one, this part gets activated in the recursive call. Then when we unwind, this is not full, so this nothing happens. Next time when we add, we go right again, and then this becomes activated, so full. And then when we unwind, this becomes activated. So next time when we add tree full, full becomes 0, full becomes 0, and then we go left. Tree is already full, full becomes 0, and then you go left. And then when we do go left, add here, and then next time we add, this tree is not full, this tree is not full, just add it to the right. And then this becomes full. Next time we add, this is not full, so this is not full, so go here. This is not full, so go here, and this. Next time we add this, fill it. And then next time we add, wait, when this gets filled, the right one gets filled. When it unwinds, this also gets filled. So when we add, oh, there is an issue here. When we add, so these two becomes full, right? But the thing is, next time we come here, it automatically goes to the left. It shouldn't. When it unwinds, it needs to undo the right part. When the tree is full, undo full. It needs to undo full, and it needs to undo rights full. What about the children of right? Okay, let's try this. If it the right full. Mm, okay, if it undoes, if it undoes this somewhere over here, and then it fills as expected, not then, well, then go right, well, as expected, right, this becomes this becomes this, and then if it's full, this becomes 0, then this becomes 0, becomes 0, then we go left again, then right. And next time, this will become full, this will become full. But the thing is, I have an idea. I have an idea. Maybe when when we set the left one to full, right subtree full, left subtree. When we set the left one to full, we undo the right on this part. Or maybe left subtree full. Left subtree is not full. Once the left subtree becomes filled, and value to left subtree. Yeah, if over here, when we unwind, when we unwind to here, we see that both of them are filled. We see that the left subtree is just filled. We undo the right. We set this to null. And then we start again. Yeah, here, 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 here. And then the right gets filled. And then this becomes this. And this, since this just got filled, we undo this. And then next time we add here, here. Here, and you go right, not left subtree full, left subtree full. You go right, right is not full. This is full. And this is full. So if tree no left subtree is full, then it would go right. Let me think this through. How about every time it fills the left, it removes the fill from the right? I'm close though. Here, removes the fill from the right. If you come here and then see both of them filled, remove the fill from here. Else if subtree is full, else if it is not full. Remove the fill from the left and then continue as before. I think I have an idea. So tree no left subtree is, if we just fill the left one, then the right one has to be empty. There. Now let's see. I need to now let's see. Start from the beginning. Not full. Fill in the left. And the next time we add, fill in the right. And then when we do add right, this gets filled full. And if this is full, set the full value to 0, go left. When we do go left, these two if conditions will happen. So next time we fill this, fill this. And now next time we add, this is here, this is full. So yeah, tree node, left subtree full. This is full. Tree node, left subtree full. Then that means we go right. Once we do go right, these three recursive calls happen again. We add here, and then next time we add here, and then this gets full. And then when we unwind from here, this becomes full. So next time when we add, this is full. So undo this, and then go left. Left is full, undo this, and then go left. And then this. And then these two happen again. This gets filled. Then when we want to add a new element, this is not full. The tree node, left subtree is not full. So we go left. Now this time it is full. So we go right and then we add an element. So next time this happens, we add an element here. This gets full. And then when we unwind, this gets full. Now here's the tricky part. You try to add an element again. Tree node, left subtree is full. Tree node, left subtree full. This is full. Wait, when it unwinds, tree node, left subtree full. Hold on, in the last unwinding part, I got confused. Hold on. Before this happens, this gets full, right? Yeah, tree node gets full. And then when it unwinds from here. In right subtree is full, so tree node full. And then when this unwinds, it unwinds from here because the left subtree wasn't full. If we add tree, when we added the node in the left subtree, when it ends up being full, the right subtree is not full. Yeah, we undo the right. And then when we add an element, this is full. So add to the right. Here. Here. Similarly again, when we come here, goes to the right, this is full, goes to the right, and then this. So when it unwinds, this gets full. When this unwinds, this gets full. And right subtree is full, tree node full. Yeah, this gets full. Then when it unwinds from here again. So this gets full. Next time, tree node full. We undo this. We just go to the, and then tree node full. Undo this, tree node full again, undo this. Come here. And then we add here. Comes like this. And then when we add a new element, tree node, yeah, this goes here, here again. And then then it goes right, and then add full. Then when it unwinds from here, tree node becomes full. And then when it unwinds from here, it checks whether the subtree is full and then undoes this. Not full again, and then it comes back here, here, full, here, here, full. Make this full, make this full. The right one is just filled, so make this full. And then when it comes back again, when you add a new element again, we wait, make this full. When we unwind, when this is filled, when this is filled, and the left one is filled. Yeah, we do go left when we unwind back to here, and then we realize that this is now full, we unfold this. You mark this as 0. So next time we come, we directly go to the right. We go to the right. You go to the right. Not tree, not left subtree full. This, no, this is full, so we go to the right. Once we do go to the right, hold on a minute. Once we do go to the right, once we do go to the right, once we do go to the right, go to right, once we do go to the right, then we go left. But why would we go left? So we do go to the right. Right is not marked as full. Left subtree is full. So go to the right, huh? I think I got stuck here. Tree node, left subtree is full. I need to somehow ignore this. If it goes to the right, should it ignore the left? It goes to the right, and if these two are filled, it goes to the right, left subtree is full. Hold on a minute. Let me think about this. It needs to somehow go left. What if I do tree node is full or both the children are full? If I do tree node is full or both the children are full, then it would go left. Set this to 0. This would work. This would work. Set it to 1. Set it to 1. This is 1. And then this right becomes 0. Tree node. Go right. Go right. Here. Here. Fill this. Here. Here. Fill this. Go back. Fill this. Go back. Hold on. Yes, go back. And when it unwinds, this becomes. And when it unwinds, this becomes. Now that the tree is full, this becomes 0 and it goes here. This becomes 0, goes here. This becomes 0, goes here. I get the left side. The left side works well. The right side, that's the issue. In the right side, when this gets recently filled, when this gets just filled, this will undo, right? But next time when it comes here, this tree is full, so it will go to the right. Because this part as well, it will go to the right. But in the right, these two children are filled. These two wasn't undone. So I should do tree dot node full or both the left and right are full. This is probably confusing too. There's probably a better way of doing this. Let me see. Enter values 5, 10, 15, 30, 40. Let me see if it just works properly. GCC test.c. My laptop is quite slow, so it's going to take some time compiling. I should have a view tree method. Void view tree. It should go left first, right? Does it cause an issue? Okay, I need to view the tree somehow. I will do a left parent right. So if tree node left subtree, if the left subtree exists, then go do the left subtree. Keep going left, 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 left. Once you have reached the end, print the value, and right subtree, right, print f, percentage d, slash n, slash n, tree node value. Okay, let me think about what this does. So it will keep going on the recursive call left, 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 left. Soon there will be no left nor any right. So it will print the value tree. When it unwinds, there will be a right to go to. So left, right. I think it would be better if I left parent right. If I do it like that. And it didn't print anything. Okay, let me see what's the issue. My Hold on. Okay, let me see what the issue is. Print F. Hello slash n. It's not able to do the thing. Or maybe I don't make a new. Oh, no, I do make a new value, right? Add a node. I do add a node. That's not the issue. Malloc new node value subtree null. What is 0? Somewhere here is the issue. Okay, I don't understand what the issue is. Uh, Prince hello, that's not the issue. I think it's the first if condition, maybe. If tree node is full, which is not. Tree node is full. Tree node is full. There is no left or right. Wait, tree node is full. If not, I think it's checking a null value. That's the issue. There we go. Uh, isn't there a boolean thing? Int what subs exist tree and true and true is undefined. How do I 0 b1 like that? I'm adding 0 b1 because I wanted to turn into a true or false value. But I think this and would work fine. and it didn't do anything. Okay. Let's see if it prints hello. Let's put a hi here. Okay, so it added the values. How many times does it say? 1, 2, 3, 4, 5. I need to view my tree. My tree. My tree. Should I be pointing up, passing a pointer? This is a pointer value. Thing is, the thing did not get added. If left subtree, go left. If left subtree. P is a pointer value, right? Is there such a thing as P? P, D. I don't think it initiated the. Let's try X. X works, right? X is hexadecimal because I can't remember. Full I add node print this printf. Okay, so wait, hold on. No, it should say it sometimes in the right, sometimes in the left. One, two, three, four, five. Why does it do that? Left subtree is null. New node. So it adds a left subtree. But why does it then say left subtree doesn't exist? Left subtree. Let's do percentage x. Left subtree, left subtree. And then the node, full node value. Node value left subtree. Why is this not working? So node, new node, malloc. The pointer gets assigned here. Left subtree. Why is this not working? Now node is initially null. Let's try new node. Just give me the pointer value. Pointer value, yes. Node. Pointer value. So, okay, wait, hold on. Node is a new pointer, but when I'm done adding this node, suddenly it doesn't. Or should I do it like this? Okay. Uh, get new node. Return new node. Return it and assign it here. Similarly for the right one. How about this? Would this work? 15.5. Where is this printing? 15.5, 30, 20, 40. I add 5 to the root, then 10, 15. Then 30, 40. 10, 15, 30, 40. 10, 15, 30, 40. Left subtree. 15 doesn't have any children. 10, 5, 10, 15. Okay, so what this is supposed to do? Five, 10, 15, 30, 40. It should print 30 first. 30, 10, 40, and then 5, 15. It prints 15, 5, 30. Where is 20? 5, 10. Oh, 20 is the root. Hold on, I got this wrong. 20 is the root. 20. Then I add 5. Then I add 5, 10. Then I add 15. Then I add 30, then 40. 30, 40. So let's see. 15, 5, 30, 20, 10, 40. Where did the 10 go? 15. So it works almost well. Um, 15 has no children, 5 has 2, 30 has none, 40 has none, 20 has 2. Why didn't it print 10? Left, current, and then left, current, then right. So 15, hold on. I need to check why this doesn't work. So 3 node left, 25, 15, 30, 25, 10, 15, 30, 40. 5, 10, 15, 30, 40. So it goes left first and then recursion occurs, goes left again, and then there's no left. So print the 15 value. There's no right. And now unwind, print 5, and then recursion occurs. No left, right. So print 30 and then unwind from there. So now that left is done, we print 20. Now that left is done, we print 20. Then we go here. We go here. We print 40. 40 from the left. Here. We go left, print 40. We go 20 and then we go right. And then when we are on the 10 node, we go left and when we end up on the 40 node, there's no left. So print 40. There's no right. So unwind. It should be printing 10, but it's not. There's no right. So unwind and then unwind. So why does it not print 10? Print 10. Print 10. Print 10. Um, if left sub tree skip tree node 5 1 2 3 4 5 5 additions, right? So right subtree. Getting so confused. Right subtree, left subtree, value. Why does this not work? Add to tree, add to tree. If I do this, what happens? Why is it stuck? Why is it stuck here? It's a binary search tree. Right. So the minimum is over there, the bigger value is over there. Uh, if we want to insert a value, RT compared to, and then go down, compare to, and then go down. we need to insert a value which is lower or higher. If it's lower, go to the left. If higher, go to the right. Like if it's 25, we go here. If it's 25 less than 32, then we go left. Or what node are they? They're talking about 30. 30. And then we unwind. Why do they call it insert help? Insert help. Note that except for the last node in the path, insert help cannot actually change the child pointer for any of the nodes that are visited. In that sense, many of the assignments seem redundant. However, the cost of these additional assignments is worth paying to keep the insertion process simple. The alternative is to check if the given assignment is necessary, which is probably more expensive than the assignment. Okay, let's use. So 51 goes in. So what am I supposed to do? 50. Oh, 66 is larger. 26 is smaller than 51. 56 is bigger and then smaller. And then 59, bigger, smaller, bigger. 28, smaller, bigger. 7, smaller, smaller. 85, bigger, bigger. 42, smaller, bigger, bigger. And then 21, smaller, smaller, bigger. Removing a node from BSD is a bit trickier than inserting a node, but it is not complicated if all the possible cases are considered individually. Before tracking the general code node removal process, we will first see how to remove from a given subtree the node with the largest key value. This routine will be used later by the general node removal function. If we want to remove this, we assign 20 here, and then this 12, and then this node points to this. It's like deleting a linked list. So this 20, so this value gets assigned 20. This is removed, and this instead of pointing to 20 is now points to 12. 20, yeah, that's what it does. Remove help. The cost of find help and insert help is the depth of the node found and or inserted. Cost of remove help is the depth of the node being removed. Or in the case when this node has two children, the depth of the node with the smallest value is in its right subtree. Thus, in the worst case, the cost of any one of these operations is the depth of the deepest node in the tree. This is why it is desirable to keep BSDs balanced, that is, with the least possible height. If a binary tree is balanced, then the height of the tree of n nodes is approximately log n. However, if the tree is completely unbalanced, for example, the shape of a necklace, then the height for the tree with n nodes can be as great as n minus 1. Thus, a balanced BSD will, in the average case, have operations costing theta log n. But the badly unbalanced BSD can have operations in the worst case costing theta n. Okay, let's see this. 15, 30. It skipped 10, 15, 30. So left, right, and then the node itself. Left is done, then we go printer. Then we go right. Where is 10? Maybe it's these two. Okay. Dictionary implementation using a BST. A simple implementation for a dictionary ADT can be based on sorted or unsorted list. When implementing the dictionary with an unsorted list, inserting a new record into the dictionary can be performed quickly by putting it at the end of the list. However, searching an unsorted list for a particular record requires theta n time in the average case. For a large database, this is probably much too slow. Alternatively, the records can be sorted in a sorted list. If the list is implemented using a linked list, then no speedup to the search operation will result from storing the records in the sorted array. On the other hand, if you use a sorted array-based list to implement the dictionary, then binary search can be used to find a record in theta log n time. However, insertion will now require theta n time on average because once the proper location for the new record in the sorted list has been found, many records might be shifted to make room for the new record. Is there some way to organize a collection of records so that inserting and searching for records can both be done quickly? You can do this with a binary search tree. The advantage of using BST is that all major operations are theta log n in the average case. Of course, if the tree is badly balanced, then the cost can be as bad as theta n. Here is the implementation for the dictionary interface using BST to store the records. We have insert, we have remove any, find, and then size. Wait, how long is this chapter? When writing a recursive method to solve a problem that requires traversing a binary tree, we want to make sure that we are visiting the required node, no more, no less. Now let's see this. Right. Where did the 10 disappear? Where did the 10 disappear? 15, 35, 40, 20. Yeah, I have another idea. Let's do print f. So my tree value percentage d, and then let's just forget this. My tree left subtree value and then right subtree value. So far, we have seen several tree traversals that visited every node of the tree, but we also saw BST search, insert, and remove routines that each go down a single path of the tree. Guided traversal refers to a problem that does not require visiting each node in the tree, though it typically requires looking at more than one path through the tree. This means that the recursive function is making some decision at each node that sometimes let it avoid visiting one or both of its children. The decision is typically based on the value of the current node. Many problems that require information flow on binary search trees are guided in this way. 25, 40. Where did the 10 go? Where did the 10 go? So 20 is, and then 5. 10 should be added on the right. Then 15, 30, then it added 40. Why did it add 40 and not 10? It did not add 10. Hmm, it did not add 10. So we know, let's try. No, I think this is going to cause an issue because there's no, it doesn't have left or right. 40 is the end, but how is 40 the end? I don't understand. Else if, I see. This is the issue. Now it prints fine. 1530. Oh no. 1530. But it's easier if I have my drawing board. 1535. Okay. 1535. Then go down. 40, 10, 20. Yeah. Finally. What is guided information? So it may skip or not skip the child node, right? The extreme example is finding the minimum value in a BST. Bad solution to this would be to visit every node. However, we can take advantage of the BST property to avoid visiting most nodes in the tree. Right. So it just skips over the larger of the child. Multiple binary trees. What is, are these only exercises? Okay. How long is, I'm checking whether I have to, I should leave some of the topics for the next frame. A hard information flow problem. Okay, I have an idea. I'll just um I will read this and then I will end the stream because I've taken a little less than 3 hours. Sometimes passing the right information up and down the tree to control a recursive function gets complicated. The information flow itself is simple enough, but deciding what to pass might be tricky. More difficult example is illustrated by the following problem. Given an arbitrary binary tree, we wish to determine if for every node A, all nodes in A's left subtree less than the value of A, and are all nodes in A's right subtree greater than the value of A. This happens to be the definition of a binary search tree. Unfortunately, to make this decision, we need to know some context that is not available by just by looking at nodes, parents, or children. I shown in figure 7.15.1. So far all of them are picker, but then we don't know this. How do we check? It is not enough to verify that A's left child has a value less than that of A and that A's right child has a greater value, nor is it enough to verify that A has a value consistent with that of its parents. In fact, we need to know information about what range of values is legal for a given node. That information might come for any of the node's ancestor. Thus, relevant range information must be passed down the tree. We can implement this function as follows. So root, compare low, compare high, compare to less than 0, compare to high more than 0, out of range. Check BTS, low root value. Return false if left side fails. Return check BTS, root value high. Oh, so that's the lower end or the higher end. Oh, I see. So In the right side, we check if we have if the range of values between root value and whatever the high is. On the left side, we check if the range of values between low and whatever the root value is. Array implementation for complete. Okay, let me read this one and then I will end the stream. From a full binary from the full binary tree theorem, you know that a large fraction of the space is in a typical binary tree node implementation is devoted to structural overhead, not to storing data. This module presents a simple, compact implementation for complete binary trees. We call that complete binary trees have all levels except for the bottom fill out completely. And the bottom level has all of its nodes built in from the left to right. Thus, a complete binary tree of n nodes has only one possible shape. You might think that a complete binary tree is an unusual occurrence, that there is no reason to develop a special implementation for it. However, the complete binary tree has practical uses, the most important being the heap data structure. Heaps are often used to implement priority queues and for external sorting algorithms. We begin by assigning numbers to the node position in the complete binary tree level by level from left to right as shown in figure 7.16.1. And an array can store the tree's data value sufficiently, placing each data value in the array position corresponding to that node's position within the tree. Table lists the array indices for the child, parent, and sibling of each node. So position 0 contains the root. Position 1 contains the two children of the root, right? Well, I need to get my whiteboard back. So, what I was saying, yeah, these two are the children of this. And then 3 and 4 are the children of 1, 5 and 6 are the children of 2, 7 and 8 are the children of 3, 9 and 10 are the children of 4. Looking at the table, you should see a pattern regarding the position of the nodes relatives within the array. Simple formulas can be derived for calculating the array index for each relative of the node R from R's index. No explicit pointers are necessary to reach a node's left or right child. This means there is no overhead to the array's implementation if the array is selected to be the size n for the tree or a tree of n nodes. So parent of R minus 1 over 2 if R is not 0. So 8 divided by 2 is 4. Sorry, 8 divided by 2 is 4. Wait, 0 plus 1 plus 2. So 0 times 2, right? So 1 times 2 plus 1 plus 2. Plus 1 is 3 plus 2 is 4. 2 times 2 is 4 plus 1 5 plus 2 6. 5 times 2 is 10 plus 1 11 plus 2 12. Okay, I see. So the children of this are here and here, here, here. And then the children of this is here and here. The children of this is let me choose a different color. Here, here. The children of this is here, here. Then let's go back here. Children of this is here, Yeah. So first is right next, and then it doubles every time, right? So there's a gap of 4 in between parent and the left child. Over here, the parent and the left child, there's a gap of 1. For this parent and left child, gap of 2. All right. Also, I just want to test one last thing. 25, 15. If I add another one here, I get 50 and then 6, 7. Let me see. 50, 6, 7. Then how do I want it to traverse the thing? 6, 15, 7, 5, 30, 20, 10. Sorry, 20, 40, 10, 50. Oh my god, it works. Okay, I will end the stream here. Next topic is about heaps and priority queue. And yeah, I will see you guys next time. Bye.